Imagine for a second that your smartphone just refused to delete any files, ever.
Oh, that sounds like a nightmare.
Right. Like every single text message, every blurry photo you've ever taken, every app running in the background at, maximum speed all the time.
Your battery would be gone in 5 minutes?
Exactly.
Okay.
You can't clear the cache, you can't close the tabs. The processor gets so hot it actually burns your hand, and eventually the whole system just completely crashes.
Yeah, a total hardware failure.
And the thing is, if you're listening to this and you've ever felt completely paralyzed by sensory overload, like in a crowded, noisy room, that exact same catastrophic hardware failure is literally happening inside your head.
It is a really phenomenal way to visualize the problem. And, what's so fascinating here is that the stack of engineering manuals and neurobiology literature we're looking at today, it completely throws out the old metaphor of the brain as this mystical biological soup.
Yeah, no more soup metaphors.
Right. We are stepping out of the chemistry lab and walking straight into a high-tech server room.
Yeah. Okay, so let's unpack this, because our mission for today's deep dive is to explore the brain not as a metaphor, but as a literal high-performance computer processor.
Hardware networks, electrical buses, logic gates, the whole 9 yards.
Right. And microscopic maintenance drones. Specifically, we're diving into a critical system failure called glutamate excitotoxicity. We're going to figure out how this glitch, how it stops the brain from doing basic self-cleanup.
And why it hoards those useless connections.
Exactly. And maybe the craziest part, how this exact same biological failure perfectly mirrors a fatal error in artificial intelligence learning.
Yeah, that AI connection is mind-blowing. And if we connect this to the bigger picture, the goal here is to understand the hardware-level reason why the brain stops pruning itself.
Like, why does it get stuck in that chronic sensory overload state?
Precisely. The central thesis we're exploring from these sources is actually quite stark. It argues that you fundamentally cannot teach a brain, or an AI model for that matter, that is currently drowning in its own internal static. It's impossible.
Wait, hold on. Let me make sure I am wrapping my head around this right out of the gate.
Yeah.
You're saying that if a person is overwhelmed, or, if an AI is failing, we usually assume they just need better training, right?
Right. Therapy, better software, more data.
Yeah. But you're saying it's actually a hardware problem?
Yes.
That.
If the hardware is saturated with noise, the software just can't run. But before we get to the glitch itself, I think we need to establish the baseline.
How the supercomputer is actually supposed to work under normal conditions.
Exactly. Which brings us to a background optimization script called Synaptic Pruning.
Right. And I know most of us have heard of that old neuroscience rule, right? Heavy in learning.
Yeah.
The whole neurons that fire together, wire together thing.
It's the classic.
Like when you learn to ride a bike, those specific pathways get thicker and faster over time.
Yes. So that is the acquisition side of the equation. When you learn a new skill, the physical connections carrying those signals are reinforced. But there is an inverse to that rule.
The pruning part.
Right. And that inverse is the operational foundation of pruning. The rule is simply use it or lose it.
Which honestly is where I get a little tripped up. Deleting brain cells sounds terrible. Why would the brain actively destroy its own wiring?
Well, because of efficiency and power management. In a healthy, optimized system, you only have limited energy.
Right, you can't run everything at once.
Exactly. So pathways that have low activity, meaning connections that carry infrequent low amplitude signals, they're identified by the system as redundant.
Just dead weight.
Right. They are taking up physical space and energy without actually carrying any priority data. So the biological operating system marks these quiet connections for demolition.
But how does it actually do that, though? I mean,
Right.
It doesn't have a little software flag. It's biology.
Well, it does have a physical flag, actually.
Wait.
Yeah. The biological OS marks these unused connections with what the literature literally calls garbage tags.
Garbage tags. I love that.
Right. Specifically, these are complement proteins named C1q and C3. You can kind of think of them as glowing biochemical neon signs that just say, demolish here.
Okay, so the tags are placed on the quiet, unused wires. But who actually does the demolition?
That is the job of the microglia.
The maintenance drones.
Exactly. You can think of them as the brain's internal maintenance drones. When the system is healthy, these microglia operate in what the engineering framework calls M2 repair logic.
M2 repair logic, got it.
In this state, they constantly patrol the neural bus, scanning the environment. And when they spot a C1Q or C3 tag, they execute a physical deconstruction of that specific connection.
Just rip it out.
Yeah, the biological term is phagocytosis. They literally engulf and digest the redundant wire.
That is wild. They just eat the junk mail.
They clear the space. And by deleting these underutilized quiet wires, the brain can concentrate its electrical power on the high-fidelity, heavily insulated pathways.
So it prevents signal leakage.
Exactly. This background optimization script is exactly what keeps the processor running fast and efficiently.
So it's like if an app hasn't been used in a year, the OS tags it, the drones come in, and they just clear it out. That makes perfect sense.
It's a very elegant system.
It is. But here's where it gets really interesting. What happens when this system is flooded with static? What happens if the OS gets completely tricked into thinking the junk is actually particle data?
And that raises the most important question of the literature. It's where we encounter the central failure we mentioned earlier, glutamate excitotoxicity.
Right, the glitch.
To understand this, we have to zoom in on how signals actually move across the hardware. In this model, glutamate is the brain's primary excitatory signal. It is the high bit of data.
Okay, so when a neuron fires, it releases glutamate across the synaptic cleft, right, to the next neuron. It's basically sending a 1 in binary code.
Yes, it sends the 1. But you cannot just leave a 1 sitting on the line.
Because then the line is jammed.
Exactly. Normally, right after that signal pulse, specialized cells called astrocytes act as microscopic vacuums.
Vacuums, okay.
They use specific transporters called EAAT2 transporters to immediately suck up that glutamate and reset the line to 0, back to ground.
So it's a really clean cycle. Fire, vacuum, reset,
Yeah.
fire, vacuum, reset.
Yes, over and over.
And that gives you the silence between the notes, which, is how you know a message is actually being said in the first place.
Exactly. But what happens if those astrocyte vacuums break down? The sources show that due to inflammation or oxidative stress or environmental toxins, those EAAT2 transporters can fail.
And if they fail,
When they fail, the glutamate isn't cleared. It just lingers in the synaptic cleft. This is the literal definition of glutamate excitotoxicity.
let me stop you there because I want to make sure the mechanics of this are crystal clear for you listening. The glutamate is just sitting there. Why doesn't the receiving neuron just, ignore it?
Because it chemically cannot. The glutamate is the key that opens the door. While it is sitting there, the receptors on the receiving neuron, specifically the NMDA and AMPA channels, they are forced to stay wide open.
Oh.
The cellular membrane stays perpetually depolarized. It is constantly, endlessly firing.
So it's not even a signal anymore. It's just a continuous screaming dial tone.
Yes. And this creates what the sources identify as the false activity loophole.
False activity.
Right. To the biological operating system, this constant depolarization is completely indistinguishable from meaningful active utilization.
Wait, really? The brain can't tell the difference between a genius thought and a broken, buzzing wire.
It cannot. The system is functionally blinded by the static. Because the connection looks so hot and active, the cell never applies those C1Q or C3 garbage tags.
Because the rule is use it or lose it. And it thinks it's being used.
Exactly. The biological OS says, wow, this wire is firing at maximum capacity. It must be carrying a massive amount of priority data. Absolutely do not delete.
So it's like a stuck check engine light on a car dashboard. The mechanic's diagnostic computer sees the light is on, assumes the sensor is actively transmitting vital data about the engine, and refuses to turn the system off, even though it's literally just a glitchy wire constantly buzzing.
That is a phenomenal analogy. The biological system is tricked into protecting the glitch. Because there are no garbage tags, the microglial maintenance drones completely bypass the connection.
They just fly right past it.
Yeah, they cannot and will not execute a pruning operation on a wire that registers as highly active.
So the pruning is only done on connections that aren't being used. But excitotoxicity fakes usage. It fakes the activity. The brain is literally hoarding useless connections because the static makes them look vital.
Exactly.
So what happens to the physical structure of the brain when it just stops deleting things?
Well, the sources describe the result as a physical rat's nest. You end up with thousands or millions of unoptimized, noisy wires.
Just a tangled mess.
And when you have that much unpruned wiring carrying constant voltage, you get massive signal bleed. You get what engineers call inductive coupling, where signals cross over and arc into neighboring wires.
Like crosstalk on an old phone line.
Right. Clinically, in a human being, this manifests as extreme sensory overload.
Because the hardware is clipping, it's maxed out. There's no headroom left to process anything new because the background noise is deafening.
Exactly. The lack of neural trimming isn't because the system forgot how to learn or develop. It's because a glutamate glitch is actively tricking the system into protecting the junk.
That is mind-blowing. And,
Yeah.
what is so striking about this deep dive is that this isn't just a quirky biological anomaly for humans. The sources point out that this is a fundamental law of information processing.
Yes, it is.
We see the exact same failure mode in artificial intelligence.
We do. If we step into the world of computer science, we see direct parallels with how artificial neural networks are trained and optimized. In AI, there is a core process called magnitude-based wheat pruning.
Okay, let's break that down. When you train a massive AI like a large language model or an image generator, it initially creates millions or billions of parameters, right?
Yes, massive amounts of connections.
The sources say it becomes over-parameterized. Basically, it gets bloated with useless noise as it tries to figure things out.
Yeah, that's a good way to put it. To make that AI actually usable, faster, and capable of running efficiently, engineers have to run a sparsification algorithm.
Okay, a sparsification algorithm.
This is essentially the AI's version of the microglia drones. This algorithm evaluates the weights of the connections between the AI's nodes.
And a weight is basically how strong the electrical connection is between 2 points in the software, right?
Exactly. The algorithm looks for weights that are close to zero. If a connection has very low electrical activity during processing, it is identified as useless.
Just like the low-activity biological wires.
Right, the algorithm sets those low magnitude weights to exactly zero, effectively deleting them.
Use it or lose it, but in code.
Exactly. This forces the AI to stop overthinking every single input and rely on its most generalized, efficient, and robust pathways. It's pruning.
But wait, how do you get excitotoxicity in a computer program? I mean, you don't have glutamate or broken vacuums in code.
You get it by simulating a chronic noise floor. If we introduce persistent random noise into the inputs of an AI, we get what computer scientists call stuck activations.
Stuck activations.
Right. Inside the AI, there are activation functions, mathematical gates like the sigmoid or ReLU functions. If you flood the system with noise, these gates get permanently stuck at their maximum output.
So they are digitally stuck wide open, just like the NMDA receptors flooded with glutamate in the brain.
Yeah.
They are outputting a constant one.
Precisely. And here is where the exact same failure occurs. When the sparsification algorithm, the AI's cleanup crew, scans the network, it looks at these glitched nodes.
And it sees them outputting maximum activation.
Yes. It registers them as highly active, highly critical pathways.
So the algorithm just bypasses them. It refuses to delete the glitch because it looks like priority data.
It has to bypass them based on its own internal logic. It is programmed to only delete quiet connections. The AI fundamentally cannot prune the redundant parameter.
They're too loud.
Right, so it begins to suffer from model bloat. The weights don't update correctly, leading to what engineers call exploding gradients, severe latency spikes, and eventual processing failure.
It develops a digital rat's nest of uncoordinated feedback. So in both the human brain and the AI processor, if the baseline noise floor is chronically high, the pruning algorithms are functionally blinded.
Yes, completely blinded.
They both misidentify excitotoxic static as critical data.
It really is a universal vulnerability in complex processing networks.
So what does this all mean? If both biological and digital brains can get trapped in this false activity loop, how do we actually fix it? I mean, if a child is trapped in a sensory overload rat's nest, you can't just leave them there.
Right, which brings us to the intervention strategy, and honestly, it challenges a lot of conventional thinking.
Glad.
The lead engineer in the NRE framework draws a very firm diagnostic conclusion here.
Okay, what is it?
You cannot teach or train a system to prune itself while it is currently suffering from glutamate excitotoxicity.
Which makes total sense, but completely upends standard behavioral approaches.
You're saying you can't just put a child or an AI through repetitive behavioral therapy and expect them to learn how to filter out the noise if the hardware itself is literally saturated.
You simply cannot solve a hardware saturation problem with a software patch.
Yeah.
Behavioral therapy relies on the hardware having enough headroom to form new, quiet connections.
Right.
If the NMDA receptors are stuck open, no amount of therapy will force the microglia to prune the wire. You must change the physical environment of the processor.
You have to fix the hardware.
Yes, You have to manually lower the gain and flush the static to achieve what the engineers call laminar flow.
Laminar flow, like a smooth, uninterrupted current of water,
Huh.
all the molecules moving perfectly parallel without any turbulence, a state of dynamic homeostasis.
That's the goal.
I love that. So how do we engineer that in the human brain? Let's walk through the technical stack intervention outlined in the sources, because they don't just say fix the hardware, they give a very specific 4-step protocol. Right, it requires a systematic mechanical approach. Step 1, you have to deal with the immediate voltage clipping. And the framework suggests using a compound called inositol to increase the signal pad.
A signal pad. So that's like putting a physical buffer on the line. How does inositol actually do that?
Well, inositol works at the cellular level by regulating intracellular calcium surges.
Okay, calcium surges.
Right, when glutamate holds that door open, calcium floods into the cell, which is what causes the chaotic electrical spike. Inositol essentially limits how much of that calcium can flow at once.
Oh, I see.
It puts a ceiling on the current, preventing the signal from maxing out and clipping.
Okay, so we've padded the signal, we stopped the spike, but we still have the broken vacuums. We still have the astrocytes failing to clean up the glutamate from the cleft. How do we fix them?
We have to optimize them by removing what is clogging them in the first place. The sources point out that inorganic EMI electromagnetic interference, often in the form of environmental aluminum, can physically clog those EAAT2 transporters.
Wait, literal aluminum in the brain is acting like static interference.
Yes, it binds to the tissues and disrupts the transport mechanisms. So the intervention uses high silica water, specifically citing Fiji water in the protocol as a solvent.
Fiji water, really?
Yeah, the chemistry here is actually fascinating. The silica chemically binds to the aluminum, creating a compound called hydroxyaluminosilicate, which the body can then easily excrete.
Oh, wow. So we are literally flushing the hardware. The silica grabs the aluminum grit, pulls it out, and gets the astrocyte vacuums working again.
Exactly.
But the vacuums also fail because the system is overheating, right, from oxidative stress.
Which is why the third component is critical. You have to deploy a heat sink.
A heatsink, like on a computer motherboard.
Yes. The stack uses NAC and acetylcysteine.
And how does NAC cool the system down?
NAC is a precursor to glutathione, which is the brain's master antioxidant. When you elevate glutathione levels, you actively neutralize the reactive oxygen species, the chemical heat that disables the vacuums in the first place.
So you're cooling the oxidative stress.
Yes, you are cooling it down. And finally, to complete the circuit, they introduce glycine.
What does glycine do?
Glycine acts as the electrical ground. Once you've padded the signal, cleared the vacuums, and cooled the system, you still have excess excitatory voltage bouncing around.
Right, residual static.
Exactly. Glycine provides a safe inhibitory path for that voltage to dissipate, returning the system to zero.
Pad the signal with inositol, clear the vacuums with silica, cool the system with NAC, and ground the circuit with glycine. That is just, it's pure, elegant engineering.
It really is a comprehensive hardware reset.
So let's bring this back to you listening to this. If someone applies this hardware reset, what actually happens inside the brain?
Well, when the noise floor finally drops below the security threshold, the line rests. Between each signal pulse, the voltage returns to ground.
The static is gone.
Yes, static is gone. And when the environment is quiet again, those microglia, the maintenance drones, experience a profound logic flip.
Because the war is over.
Yes. They flip from their M1 attack logic, where they are highly defensive and reactive to the inflammation, back to their M2 repair logic. And in that quiet, clean room environment, they look around.
And what do they see?
Well, without the glutamate static holding the door open, those old, redundant connections suddenly look very, very quiet.
And because they are quiet, the false activity loophole is closed.
Yeah.
The biological OS realizes they aren't actually being used.
Exactly. The OS finally applies the C1Q and C3 garbage tags. The microglia see the tags and the pruning resumes.
They finally get to work.
They physically deconstruct the rat's nest. The crosstalk stops, the signal bleed stops, and the processor achieves laminar flow.
So what does this all mean for someone experiencing severe sensory overload or, for parents trying to help a child who is struggling? It means we shouldn't view the brain as permanently broken.
Not at all.
It's just clipped.
Mhm.
We don't need to rebuild the patient from scratch,
Yeah.
and we don't need to force them through agonizing behavioral drills while their brain is on fire. We just need to drop the noise floor so their own maintenance drones can finally do their job.
It shifts the entire perspective.
Right.
We move away from trying to force a behavior onto a system, and instead, we simply provide the hardware environment where the system's own inherent intelligence and optimization scripts can reemerge.
It's amazing.
The brain wants to heal, it just needs the silence to do it.
That is incredibly helpful. To wrap this all up, the key takeaway from this deep dive is a total reframing of how we view learning and neurodevelopment.
Yeah.
A lack of neural trimming isn't always a structural deficit.
No, it's often a symptom.
Right, very often it's a false activity glitch driven by glutamate excitotoxicity. Excitotoxicity fakes usage, and because the system only deletes unused wires, the pruning stops. Whether you're looking at a human brain struggling with sensory processing or you're trying to optimize an over-parameterized AI model, excess noise blinds the system's ability to clean itself. The secret to learning and processing isn't just about acquiring new signals, it's having the deep, fundamental silence necessary to delete the old ones.
And if we connect this to the broader reality of our modern world, it leaves us with a rather profound thought to ponder.
Oh, I'm ready.
If our biological brains absolutely rely on this quiet time between signals, this return to ground, to identify what is actually important enough to keep, what happens when we live in an external environment that constantly bombards us with high-bit digital noise?
Oh, wow. I see where you're going with this.
Are we artificially inducing a state of digital excitotoxicity in our own minds? By constantly scrolling, by constantly leaving the TV on, by never letting our own cognitive inputs return to zero, are we functionally blinding our internal algorithms?
Stopping our own brains from pruning away the useless information.
Exactly. Are we preventing our own minds from cleaning up the junk of modern life?
We might literally be trapping ourselves in our own digital rat's nest. It really makes you think twice about your environment, doesn't it? Take a look at the static buzzing around your own hardware today. Thanks for joining us on this deep dive.